Hello. So I'm going to talk about a thing. I already talked about SPLS, but I'm not sure what the intersection is, so I'm just going to talk about it again. So this is an algebraic approach to type checking and elaboration. So the idea is I'm going to try and, rather than just come up with an algorithm for talking about how to do elaboration. So elaboration is turning source text into some kind of core typed language in a way guided by types or inferring types or inferring terms or whatever. We're trying to do it as an algebraic approach, and hopefully the algebraic approach can guide things and also try and build a bridge between type inference and programming languages and proof assistance and things that work that try and help you write proofs. Where people are interested, and now proofs are so huge you want to do things like refactoring proofs. So I hope an algebraic approach can tell you when two proof scripts are equal, not when two proofs are equal, but when two scripts that are generating proofs are equal. So to do this, let's start writing a type checker. So I'm going to write a type checker for a simply typed lambda calculus. There's only going to be three base types, A, B, and C, and then there's function types here, types to types, types here. I'm going to use sort of textbook style Haskell, the one you can't type in, so you can't actually try it for yourself. You have to learn how to translate textbook Haskell into ASCII Haskell before you can learn. But this looks nice on slides. These are the terms. There's just variables. I'm going to use Brownian indices to represent variables. This int here should be an actual number. It refers to the number of lambdas you have to climb up to get to the binding variable, or the binder. I've got lambdas and we've got applications. So it's just going to simplify lambda calculus. And a type checker has this type in Haskell. So it takes a term, it takes types representing a list of types for the types in the context, and it maybe gives you back a type. If it gives you back nothing, then that means your term was not well typed. And then we just work our way down different term constructors. We can type check variables. We just look up the variable in the context. We're assuming here that all, well, I'm assuming, you can assume what you like, but all these terms are going to be well scoped. So I'll come back to that later. At the moment, we're going to assume that for every variable, there is a type for it in the context. And then for lambdas, what do we do? Well, we've explicitly typed the lambda abstraction here, so we just add that type to the context, and we type check the rest of the term. If it actually gives us back some type for the body, then we return back the arrow type. If it fails, then the whole thing fails. And for application, it looks complicated, but that's just because we've got two subterms. So we're type checking the application of the function represented by term 1 to argument represented by term 2. So we type check term 1 in the context. If it's a function type, then we type check term 2. If its type matches the domain type of the function, then we return type 2. Every other case, we just fail and return nothing. So this is a simple type checker. You might have done it in a sort of learning Haskell course where you write some kind of type checker for not Haskell. But let's try and take this type checker to bits to see how it's built up and how to sort of reconstruct it in an algebraic way, so we can learn a bit more about how type checkers work. So I'm going to keep the same range of types as before, so A, B, and C, and arrow types. And now we're just going to abstract out what is a type checker. A type checker is something which is going to take a list of types representing the three variables and return maybe a type. So here it's not just talking about terms anymore, it's just a thing which takes types for three variables and gives you back a type for the whole thing. And now we can take the bits of the type checker we had before and put them and just call them little type checker components. So we've got the type checker component for doing variables. That's something which takes an integer, which represents, well, not an actual number, which represents the right variable, and it takes a context and just does what the previous one did. It returns the type for that variable. The lambda one, it takes the type and the subtype checker representing the rest of the term, and it passes the extended context to the subtype checker and then does the same thing as before. And the application, well, now it's a combinator that takes two type checkers, puts them together and gives you another type checker, and it just does the same thing as before. It takes term 1, takes type checker 1, passes the context, if it gets back the function type, it passes the context back into term 2, and if the domain types match, it returns type 2, otherwise it fails. Now we can sort of, one particular way of putting these back together is we take our old term data type and we actually write a type checker which just works for terms. So we just sort of do the sort of holomorphism on the terms. We take variables, we use the variable type checker, we take lambdas, we use the lambda type checker, we take applications, and we use the application type checker. And then we can write type checker scripts. So instead of writing terms, which then we throw at the type checker and we haven't got any choice about what gets done, we can use the bits of the type checker, and we can now think of when we're actually writing a term, what we're doing is scripting a type checker. So if we wrote down this term in the source language, then really the type checker was running this script. It was running, let's do a type checking process for lam a to b, then a type checking process for lam a, then a type checking process for application, and a type checking process for variable 1, and a type checking process for variable 0. But now we can also think about, well, how can we type check terms which happen to have holes in? And now this is a sort of a family of type checkers, sort of parameterized by this x here. So this x here is not the object lambda, this is the meta level lambda. And we can sort of type check, write type checker script for this kind of term with a hole in. And not only can we write type checker scripts, we can add new kinds of sort of type checking primitives that we didn't have before, that we didn't have access to in the source language. So we've got, again, types and what a type checker is, but we can now write a type checker that always fails. We can always just return nothing. We can have a type checker that says, I would like to sort of introspect on what the current variable's types are, something that you can't usually do in a programming language. You can't say, oh, hang on, I know I've declared x previously, but I'd like to just now check that x has type int or something like that. But you can do that in sort of tactical theorem provers, where you can say assert that something has the right type. But now we can have a little type checker script that's given a subterm and a variable name and a type. We can check that that variable currently has that type, and then we carry on type checking with the context, otherwise we fail. We can also check that the thing that's currently being checked has the right type. So we say something has type. If when we type check it and we return it, we check the two types are equal, and then we just pass through the type, otherwise we fail. So now we can write terms that have assertions. So we can actually write as a term the property that it has the type A arrow B arrow A arrow B. And so this is this kind of, just in the combinators that I've shown you, we can sort of write this just as one kind of type checker script. And we can even write terms with a hole again, and also they've got assertions again. And we can write two assertions, and then we get all the way down here. We may have forgotten, if you think you were writing functional programs, but often we're writing them in an imperative style where we're updating the context. As we go under every binder, we're updating the context, and sometimes there's more complicated things like constraints going on. And sometimes it's difficult to keep track of what types things have, things like that. So we can just make assertions as you would in an imperative programming language. You would say, assert the invariance of my red-black tree at this point. We're just going to assert that, I mean, the variable 1 here, so meaning this one here, actually has type A arrow B. Maybe this is a much larger program, and we've lost track of what this thing here is, or we're doing some pattern matching, and the type is transmutated through some kind of unification. So I've given you some basic operations of type checking, and now it's interesting to think about, well, what are the laws of these basic operations? So we can sort of abstract further. Just we had this previously. I had this type checker type. We took a list of types and returned maybe type, and some operations. We can sort of abstract further and just say, well, let's have a type checker class. I'm not even going to say what the implementation is of the type checker. And it's going to have these operations. So these ones over here that are the operations which allow us to sort of type check terms, as we did before. And over here, these kind of commentary on the type checking process as it's going along. And now we can think, well, what are the laws that these obey? So somehow we're going to think that none of these are going to interact in any way, because we're not yet talking about the semantics of the programming language in terms of the way that you write down var, lam, and app in your source language, and they don't interact in any way. They just sort of sit next to each other being syntax. However, the ones on the right do interact with the ones on the left, and the ones on the right interact with each other. So failure is contagious. So if we've got failure, then it doesn't matter where it appears in the term, it's always going to bubble up to the top or down to the leaves. We have these equations that sort of say what happens when we have assertions about types. So if we have a lambda abstraction, then we're asserting that the zeroth variable, that's the one that's bound by the lambda abstraction, has the type A. If we've got some assertion, then we can push it past the lambda and say that, well, we just have to bump up the index by 1. If we have some assertion, then we can push it inside an application. If we have some assertion, then if we know that that variable has that type, then we know that the whole term has that type at that point as well. We can turn, knowing the variable has a type, and we use that variable, we can turn that into the whole term having a type. And then there's some commutation ones. So if we assert things twice, the same as asserting it once. If we assert two contradictory things about the same variable, then that's a fail. And if we assert things about two independent variables, then we can reorder them. And then for has type, this is kind of information being pulled back out of what the terms type. So if we know we're doing a lambda and the body has type B, then we know that the whole thing has type A arrow B. If we know we're doing an application and we know that the function part has type A arrow B and the argument part has type A, then we know the whole thing has type B. And if we get it wrong in the application, then we fail. And again, we have this kind of, we make the same assertion twice, and that's the same as making it once. And if we make two contradictory assertions, then that's going to be the same as failure. So now, it's possible to prove a theorem that says that these equations actually capture the type checking rules. So if we let, for any term t, any closed term, if we let t be the translation into the sort of type checking theory, so we translate all the variables using var, all the lambdas using lam, and all the applications using app, then if that term is well typed, if and only if that term is well typed, then we assert that the whole thing has type A, the translated version, and it's not equal to failure in the type checking theory. I think what's nice here is that, I mean, it captures type checking in this way, and also it gives us rules for how we can move things around inside the term. So we've got these kind of proof scripts you might write in Koch or Isabelle or something, that you can put assertions in, but you're not quite sure what effect they have on the proof state. Are they affecting the underlying proof term that's being generated? What equation? What rules can you use for refactoring proof scripts? Do you just sort of fiddle with it and then, well, you don't do that further. You commit it to version control, then you fiddle with it, and then you work out whether it works or not, and if you roll it back if that didn't work. But now we can sort of start to think about actually thinking about proof scripts as real things. Now, but we can go even further. Because there's an algebraic theory, once you have that, your first thought should just be monad. I mean, there should be, well, no, it shouldn't be your first thought anyway, but you have an algebraic theory, and we think, well, what can we do with this that allows us to extract the most power out of it? So what I've done here is taken all the operations, var, lam, and app, have, has, top, and failure, and added a return that stands in for variables. So we now have two types of variables. We have the variables of the object language, and we have variables here which stand in for type checking processes we don't know about yet. And this is a free monad, and here's the bind operation. The bind basically just substitutes things in. For every time there's a return, we can substitute something in, so we can build up bigger and bigger type checking scripts. And now, so for any alpha, TC term is the free type checker algebra with no rules. And we can build up some sort of handy combinators from the constructors I showed you on the previous slide. So var with the capital V, lam with the capital lam. And then we can write type checker scripts rather than that kind of continuation parsing style I was writing before. They start to look more now like tactic scripts. So we're going to write, this is actually generating a well-typed program as it goes in a kind of declarative style. So we're saying the goal is that we want to prove that A implies B implies that A implies B. We do this by having a new sort of variable abstraction that has type A implies B. We have a new variable abstraction A. We're asserting now, we're not quite sure what's going on, so we're definitely going to make sure that variable 1, so this one here has type A implies B, and variable 0, this one here has type A. We're going to restate that the current goal is B, and we're going to fill that in by saying, well, now we can apply variable 1 to variable 0. So it starts to look very similar to how you might write a script in something like Koch or Isabelle. So I was a bit hazy before about what happens if we have variables which are out of scope. So there's two ways of dealing with that. One is to index everything by a natural number, telling us how many variables we're allowed to use. And then on the var one, we use spin n, so that just means any natural number less than n, essentially. And every time we go under a lambda, we add one to the number of variables we're allowed to use. This gets rid of this kind of partiality that was there before. So alpha n, if alpha is a class type checker, is a type checker in a context with n and 3 variables. The same equation before. However, this isn't very easy to use. We have to constantly track the number of variables we've got in scope, and it appears in all the types and everything. So another way of doing it is to use higher order abstract syntax. So here, we have type checker class has 2 type variables. One is new, stands for variable, because it looks like a V, and alpha, which is the type checker itself. And we're using this to stand in for variables themselves. So the var takes a variable to a type checker, lam gives you a new one here, so this sort of appears in a negative place, so it gives you a new variable to play with. And the have one takes variables as well, and it turns out if you quantify overall new here, then you get the right scoping rules. We have to change the way that the free monad works just by using new here rather than int, and using a new here to introduce it. The bind works as before. But now we can write type checker scripts that start to look a little bit nicer. We don't have to refer to the Broyn indices for variables which have been introduced. We can refer to them by names in the meta language. So now we can say the goal is A implies B implies A implies B. We're going to have a new variable v1, which has which has the meta name v1, which has type A implies B, or a new variable A, so v2, which has type A, and then we have the sort of same assertions as before, and now we can refer back to them using the names v1 and v2. Now, if we replace lam with introduce, or intros, as you might have seen in Coq or something, and if we replace var with assumption, it starts to look more and more like we're actually writing proof scripts, we're writing things which generate terms in a nice way, which are sort of interplay with the type checking process. So we're simultaneously making assertions about the type checking process and generating the proof terms for part of the type checking process. So I abstracted away from what's the actual implementation of the type checker. So previously I said it takes a list of types and gives you back a maybe type, and then I just made it into a type class. Now we can evaluate type checker scripts. If we say that we have no kind of unresolved holes left in the type checking, we can evaluate the whole thing, and then this sort of plays out back into some implementation of the type checker. And if we instantiate it with, takes a list of types and returns maybe type, then we get something that checks types for you. If we instantiate it with, in this sort of faux Idris syntax, then we can have something which actually generates well-typed terms at the end. It takes a type checker script. As long as that type checker script doesn't return fail, then it actually gives you back a well-typed program. And then starting from here, so you've actually got, at least for the simply typed standard calculus, we can write type checker scripts which generate terms. We can start thinking about, well, what are the type systems? So Connor mentioned using bi-directional type checking to push types into the terms. And this stacks really well here, because now, instead of terms sort of sitting there and having types pushed at them and then go tutting when they fail or something, the terms can fight back. They can look at the type and they can change what they're going to do. So we have type checkers which can either be in the checking or the synthesis stage. The variable synthesizes because it gets it from the context. The lambda, we have to check the body, but we no longer have to type the variable here. We check the body, and then we get, because we're going to push the type in, so we know what the type of the variable is going to be, and we get something where we can check the type at the end. And application, we synthesize the type of the function, and we check the type of the argument, and we synthesize the result. We need something to switch directions. This is the COD thing from Connor's talk. And something to ascribe. This is the doc one. And again, we have the fail, goal is, and have. And a have works in either direction because it's just looking at the context. There's no difference in the context of whether or not we're checking or synthesizing. And here's how we might implement this just as the type checker. The checker takes a list of types in the context and the type is meant to be and returns yes or no. Synthesis takes a list of types in the context and returns maybe some type. But now we can write terms that are active in the environment they're being type checked in. So we have a script here where we no longer have to put type names here, so we just introduce two assumptions. We find out what the current goal is, and then depending on what the current goal is, we can return two different things. So this is was sort of introduced in the context of object-oriented programming by this paper by Omar et al. At eCoop last year, where they were interested in having syntax for literals, where the interpretation of that literal, so let's say a piece of HTML or a piece of SQL or something like that, the interpretation of a literal depends on what type of program the rest of the program demands it to be at that point. So we can mention some elaboration function which taking some polymorphic constant, it's just a string, we look at the goal, and if the type is A, then we interpret that string as something of type A. If it's B, we interpret that string as something of type B. Another extension we can make following, so there's this nice paper by Sam Staten at the FOSSACs a couple of years ago where he gave an algebraic presentation of essentially Prolog. So again, we have this kind of higher order abstract syntax thing, but now in the types, we're allowed to have meta variables which stand in for types we don't know yet. And as well as the things we're actually using to construct the term, we're also allowed to say, I'm just going to make a sort of stand-in here for a guess that I don't know how to make yet. So I'm going to make a new meta variable, and given two types, they can be unified, and this may fail or it may not. If it doesn't fail, then we carry on with the knowledge that these two things are unified. Now we also have things which, so now instead of requesting the type of an individual variable, this gives us all the variables and their types, and the thing that we can ask what the goal is. And now we have failure. We also have choice, so we can write programs which backtrack. Sorry, we can write type checker scripts which backtrack and allow us to make different decisions about how the type checking is going to proceed. So now we can write programs which not only can they look at the goal, they can also look at the context, and they can backtrack and make choices about how to actually construct the program just from looking at the types. So we can say by assumption, so we get to the end of a long program and we think, well, of course you had to fill this in, I've already done it somewhere in the context. So we can just say, look at the goal, we get the context, then we write this little research thing to look through the context. If we get to the end of the context, we haven't found anything, it fails. Otherwise, it tries to unify the goal type with the type of something in the context. If that works, then it returns it and uses it as a variable. Otherwise, it carries on and searches the rest of the context. We can start to write little tactics by building up these combinators for building a type checker script. So that's the end. So I think the main point here is if you take a type checker apart into little bits, and then you can stick it back together in different ways, and then the ways you're allowed to stick it back together can actually become your source language. And then we can reinterpret things that used to be type checkers as now as elaboration scripts, because they can start to look at the types of their free variables and types they're expected to be. And it's this kind of idea of active terms which can respond to the typing environment. I really don't know whether this works for more complex type systems. So you might well say, well, this works for the simply typed dynamic calculus, that's all very well. But does this work for anything which involves dependent types or polymorphic types or anything like that? I don't know. What are the right operations and equations in general? So this set, I mean, there's a theorem now that says that this is sounded complete for actual type checking, but are they the right ones you want to use for doing proof refactoring? What are the free algebras? So I've given you a couple of implementations of the type checker algebra which satisfy the equations, but is there one which does just the equations? I mean, you might imagine it just corresponds to the well-typed terms. Does it actually work? Is this a sensible way to implement type language? And yeah, in relationship to tactic scripts, so high proofs is one interesting thing where it's a kind of hierarchical structure of proofs. You set out a kind of overall structure for how to do a proof, and then you fill it in can that be done in a style but using sort of just normal lambda abstraction to talk about vectors? And is there any connection with hygienic macros? The fact that I had to do some method for keeping track of what the free variables are, either using HOAS or De Bruijn indices. But can we now have macros which are type sensitive? Can we have macros that do the right thing depending on the type they're being instantiated by? Thank you, that's it.
Any questions?
Yeah. So you had things which gave us a maybe answer, where we were expecting to say either here's your type or doesn't have one.
Yeah.
But sometimes you have situations where it's not where the answer to the question you're working on isn't obvious yet, but it might become obvious later.
Yeah.
So is there scope for kind of more interesting suspended semantics?
I think so, yeah. So I've experimented with taking the thing from Adam's thesis, where rather than returning maybe, it returns a set of constraints. And due to the way they get sort of threaded through, yeah, some things are suspended. So you know what you get back an elaborated term which has meta variables in it, and a meta context that's got a list of problems you still need to solve. And I guess once you get back up to some relative top level, if you haven't solved all the problems yet, then you report that, otherwise you just carry on and hope you solve them in the future. But yeah, you can do that kind of thing. One thing I'm not sure about is exactly how the backtracking works, because it's kind of obvious in something like Prolog, where I talked about there. If unification fails, then you know you have to backtrack. If unification hasn't failed yet, but it might do in the future, you may sort of lose the context you were doing the backtracking in. So I think, yeah, I'm not sure how it works with this idea of choice, and the fact that the choice combinator I had here is kind of constrained by the structure of the term you're working in as well.
Yeah, it'll get a bit transactional at that point.
Yes. Yeah.
So, yeah, you've got the open question. Does this work for more complex type systems? Have you tried just pushing a little bit in any particular directions?
So I tried doing it, well, okay, so I'm say what I did try. So I tried doing it for I think the normal style one, which would be on the meta variables, and that seems to work quite well. I then tried to implement it for F omega, because I thought that would be simpler than doing dependent types, and it turns out it wasn't.
What about just systematic?
I haven't tried that. No, I wanted to do something where there was actual kind of interesting computation at the type level. So yeah, trying to use Adam's thesis, and it's entirely my own fault why I haven't managed to do that yet. I thought it would be simpler to try and translate it into F omega and then carry on, but I mean the fact we've then got 3 syntactic categories of things actually just makes things worse.
So it's like it might actually be easier to do type theory than FOA.
So you looked at failure, you looked at continuations at all, like shift use?
Yeah, I don't know. So I guess there is a kind of choice is a kind of if this one fails, then do this one. But whether or not there could be some kind of built-in exception handling mechanism where you try something big, and if that all fails, then and also, I mean, this failure is sort of contentless. So it could return, so these equations, where is it? The equations that said, yeah, these equations that said failure was contagious, the failure that happens inside a lambda could then turn into a failure that told you it was inside a lambda. So it could actually sort of invert the context it was in to tell you where the problem was.
On your by assumptions thing, so there's sort of a side affecting the choice in there, right? That's the first thing that could possibly unify with your goal on the side of that was the thing
Yes.
unified with your goal. And potentially that could have been the wrong choice, right? So have you,
Yes, agreed. But then,
you thought about how to sort of integrate backtracking at that point to try.
well, yeah, so that's what I was saying about the backtracking is constrained by the shape of the term. So if it was the case that you made the wrong choice there and then something else finds out about it, then it can't backtrack that far because the backtracking has to happen. So somehow the var, lam, and app are kind of rigid within the backtracking shape. You see what I mean? So yeah, so there is a kind of potential problem with the backtracking in that it has to be kind of local within that point.
Okay, the third page of equations. So you're, I can't tell if your rule for functions is stronger than it needs to be. So,
Oh, because it has that in there.
well, no, I just wrote the style. It's fine.
Okay, then saying this speaking.